Hello everybody, and welcome to example 2. We are still looking at page 136 of the workbook here. And they're asking us to kind of use the method that we developed in example 1 to solve a problem here. And let's read this example together. So they're starting by noting that this set S that they're giving us is an orthogonal subset of R2. Remember, since we're in R2, we're assuming by orthogonal that it's relative to the standard inner product, the dot product. So this is an orthogonal set because the dot product of the two vectors in it is zero. And they'd like us to use the strategy of example 1 to write y equals 1, 4 as a linear combination of those vectors in S. Okay, so linear combination again just means that we're going to try to take that vector y. We're going to try to find some coefficients that build it as a combination of the two vectors in S. Okay, so we'd like to solve for a1 and a2 so that this equation is true. Okay, now just a comment about this. We've already solved problems like this way back earlier in the course. We discovered we can solve a problem like this using a system of equations. Okay, that's kind of the standard approach. But they're asking us to use the method of example 1. It's a very different approach for finding these coefficients. Okay, and in particular, it's asking us to use this formula up here using inner products to find those coefficients. Okay, so let's remind ourselves of what the VJs are. Those are just the vectors in the set that we're given. Okay, so V1 would be 2, 1, and V2 would be 1, negative 2. Now we're going to use this formula up here to calculate the AIs. All right, so let's start with A1. Okay, so according to this formula, A1 is going to be the inner product of y, which is 1, 4, with V1, that's 2, 1, over the norm of 2, 1 squared. And remember, we're in Rn, so we're assuming the standard inner product here. So in the numerator, we're just taking the dot product of 1, 4, and 2, 1. That's going to give us 6. And down in the bottom, let's see, the length of 2, 1, that's just going to be the square root of 2 squared plus 1 squared. That's the square root of 5 squared. So do with those calculations, and we're going to get 6/5 for that. Okay, there's our first coefficient. And A2, same idea. Okay, according to the formula at the top of the page, this time we're going to take the inner product of y with V2. Okay, over the length of V2 squared. And this time, let's see, if we take the dot product in the numerator, we're going to get 1 minus 8 is negative 7. Okay, and the bottom length squared is going to be the square root of 5 squared again. Okay, so this time we get negative 7/5. Okay, and so if we've done all of that correctly, here's what should be true. That vector y4 that we started with should be equal to our first coefficient, 6/5 times V1 minus 7/5 times V2. Okay, and I'll leave it to you just to maybe verify that that's a true statement. That actually works mathematically. Okay, now I want to make just one closing comment. We've finished the problem here. We've done what they asked us to. I want to just contrast the two methods, okay, that we did here. Okay, so solving a problem like this of finding coefficients, there's the old way of doing that, which involved using systems of equations. Okay, we did not do the problem that way, but we could have. Okay, and the second method, the way that we did the problem, involved inner products using the formula up here at the top of the page. Okay, so we've got two different ways that we can talk about doing this problem, and so a natural question to ask is which way is better out of those two? Okay, well, it turns out that it depends on how big this value is here, the 2. I'm going to call that n. Okay, so that just measured the size of our tuples, basically, and in R2, probably doesn't make a huge difference which of these two methods you use. I think you would find that the amount of work is similar, might actually even be a little easier using the system of equation approach. Okay, but here's the key observation. If the value of n is large, okay, if we were talking about 100 tuples or 1,000 tuples or 10,000 tuples, which is not that unusual of a number in applied problems, turns out that the inner product method, that way of doing this, is much more efficient. Okay, for those of you computer scientists out there, you talk about algorithm complexity. Using the inner product method is a big O of n squared algorithm, and systems of equations is a big O of n cubed algorithm. Okay, so for big problem sizes where n is big, if you were going to program a computer to do this, using inner products is a much more efficient way of solving this problem. Okay, and I'll leave you with one thought. To be able to use method 2, we need an orthogonal subset, so that's why it's so important to be able to find an orthogonal subset. And a lot of the rest of the section will kind of address that problem. How do we do that? How do we come up with an orthogonal subset?